Welcome my friends, welcome to my next lecture. Now for today's lecture, my plan is to talk two beautiful theorems once again in complex analysis. One of them is Schwarz lemma and another is Morera's theorem. You will see in my last lecture I discussed what is called maximum modulus principle or minimum modulus principle, or same as maximum modulus theorem and minimum modulus theorem. Couple of its consequences I have discussed, some examples I have discussed. Now you will see today I will talk about Schwarz lemma. It is the proof. When I will talk about the proof of Schwarz lemma, you will see it will be very nice applications of what is called maximum modulus theorem to conclude Schwarz lemma, and at the end I will talk about Morera's theorem. It is like converse of what is called Cauchy-Goussard theorem. So that's my plan for today's lecture. So I'll start with the statement of Schwarz lemma and the proof as an application of what is called maximum modulus theorem. Okay, so as I said, let me start with the statement, but before that, this is the famous mathematician Schwarz. It's a German mathematician. Okay, so Schwarz originally studied he was a chemist, I should say. He was a chemist, then he moved to mathematics. But he is expert in many areas like complex analysis, differential geometry, calculus of variations. But in complex analysis, due to Schwarz lemma, he is very well known for complex analysis. Okay, let me just see the statement first. Okay, so this is Schwarz lemma. What is that? So the following result I have written, the following result is a consequence of maximum modulus theorem. Let me state the theorem. What is the statement of this theorem, Schwarz lemma? It says that, okay, you start with the open unit disk. So that means this is my D, Z belongs to C, mod Z is strictly less than 1. Suppose this is an open unit disk, and suppose you have a functions let f from D to D is an analytic functions. So it is an analytic functions on D but taking values in D also. That is very important. Okay, with the fact that f vanishes at 0. Of course 0 belongs to that set because it is an open unit disk. It's an open unit disk with center 0, radius 1, right? So that means start with an open unit disk. Suppose f from D to D is an analytic functions which vanishes at 0, then you will have two conclusions I can give. One, that I can estimate my modulus of f of z which is dominated by mod of z. That means I can have the what is called growth of f. You can in that way you can think about that. So growth of f or the estimations of modulus of f is dominated by modulus of z. That means growth of f should be like growth of the kind of polynomial z. So like if I think about the growth of f, so if I define g of z is equal to z, that means growth of f is dominated by growth of g. Not only that, the derivative of f at the point 0, if I take the absolute, it is dominated by 1. Moreover, if I assume that suppose modulus of f of z is equal to modulus of z for some non-zero number z in D, or say absolute of f prime 0 is equal to 1, then you have the precise expression of your functions. That means your fz has to be a times z, where a is a complex number with unit modulus. So therefore the Schwarz lemma is very nice in a sense that if I have a analytic functions from open unit disk to open unit disk with the fact that f of 0 is equal to 0, then I can talk about, so that means what I'm saying is that this kind of functions has some specific properties, not like you have plenty of functions which are having that kind of properties, which is analytic from open unit disk to open unit disk with center 0 with the fact that f of 0 is equal to 0. It should satisfy certain conditions. What sort of conditions? I can estimate the growth of f in terms of the polynomial. That means modulus of f of z is dominated by modulus of z, and second is that the derivative of f at 0 should be dominated by 1. In particular, if I assume that modulus of f of z is exactly equal to modulus of z for say some point z naught in D, or say modulus of f prime 0 is equal to 1, then you have the explicit expression of f. That means your fz of the form a times z, where a is a complex number, modulus a is 1. So that means a very specific kind of f satisfies the properties that f is analytic from open unit disk to open unit disk with the property that f of 0 is equal to 0. That means Schwarz lemma somehow characterizes what sort of functions you will have if you have the assumption that f is analytic from open unit disk to open unit disk with the fact that f of 0 is equal to 0, then it says that you have very less number of choice. That means your function's growth should not exceed the growth of the function g of z is equal to z, and the derivative of f at 0 is less or equal to 1. And in particular, if I say that absolute of f of z is exactly equal to mod z for some z in D, or say absolute of f prime 0 is equal to 1, then you have the explicit expression. That means your f of z is exactly equal to the polynomial of 1 degree polynomial, that means a times z, where a is a complex number with unit modulus. That means somehow it characterizes the all analytic functions from D to D having the property that f of 0 is equal to 0. Okay. Now you will see, as I said, it is a very nice application of maximum modulus theorem. So to prove that, proof will be very interesting. Look, so proof of Schwarz lemma. So let me go through the proof very in details. I am going through the proof. Okay. So what I want, so I have the assumption that it is just analytic with the fact that f of 0 is equal to 0. Then I will conclude these 2 points. That means absolute of f of z dominated by modulus of z for all z in D, and modulus of f prime 0 is dominated by 1. Okay. So what I am doing is that since f is analytic in D and f of 0 is equal to 0, I am defining a new function or auxiliary function, that is g of z, which is f of z divided by z if z is non-zero. And now what is this? F is analytic, that means f is differentiable at the point 0. Then I am saying that at z is equal to 0, the limit should be f prime of 0, because you see, if I calculate the limit z approaches to 0 f of z by z, what is that? This is limit z approaches to 0 f of z minus f of 0 divided by z minus 0. Why? Because I am assuming f of 0 is equal to 0, right? So, and what is that? This is the definitions of derivative of f at the point 0. So, therefore, this is f prime of 0. So, therefore, since f is analytic at on D, so therefore, it is differentiable at the point 0. So, therefore, at 0, I am defining a function g which is f prime of 0, and if z is non-zero, I am defining fz by z. Okay. Once I have this function g, then you see this kind of function is very nice functions. Why? Because at z non-zero, what kind of function it is? F is analytic function, it is given, that means it is analytic on D, right? Numerator. Denominator is z, z is non-zero, that is also analytic function. So therefore this portion is analytic if z is non-zero. And by defining that at z is equal to 0 f prime of 0, that means, so only part where the function g behaves very badly, it's the point z is equal to 0, because z is equal to 0, you cannot have like fz divided by z, does not make any sense. Like if z equal to 0, it blows up. So therefore if z not is equal to 0, the function g is nice function, it is analytic functions. But only at the point z is equal to 0, it makes a problem. But since my functions f is analytic on D and it is differentiable at the point 0, and by defining g at z is equal to 0 f prime of 0, I am removing the singularity at the point z is equal to 0. Now the way I have defined the function g, now it is a very nice function, it is analytic function on the whole disk. So therefore it's see, we first show that g is analytic in D. So if I take out the origin from D, then there it is analytic, because it is of the form fz by z and it is the quotient of two analytic function, it is perfectly alright. But only problem it will face it at the point 0. Now clearly g is analytic on D by 0, because it is of the form fz by z and both of them are analytic. So only problem you will have at the point z is equal to 0, but since f of 0 is equal to 0 and my functions f is analytic at the point 0, so therefore f prime of 0 I have just said, so this is nothing but limit of z approaches to 0 fz minus f0 divided by z minus 0, which is nothing but limit z approaches to 0 fz by z. So therefore if I define limit z approaches to 0 gz, which is nothing but f prime of 0 and which is same as g at of 0, if I define like that, then the apparent singularity, which you can think about that there could be a singularity at the point z is equal to 0, but I can remove it. That kind of singularity is called removable singularity. So I am removing. When I will talk about singularity in my coming lectures, then you will see, even though a priori you are thinking that at the point z is equal to 0, the function g might have some singularities, but by defining g of 0 is equal to f prime of 0, I am just removing that singularity. That means at the point 0 also it is analytic. So therefore I am removing, so z is equal to 0 is removable, and hence g is analytic throughout the domain. So G is analytic, D minus 0, it is perfectly alright. So only at the point 0 where you might think it will the point 0 will have the point 0 is a singularity of the function g, but by defining g of 0 is equal to f prime of 0, I am removing that singularity, and therefore the way I have defined my function g, which is actually analytic on my full domain D. Okay, so that is the first step. So given the fact that f is analytic from D to D with the fact that f of 0 is equal to 0, if I define this function g, auxiliary function g, which is of this kind of form, fz divided by z if z is non-zero and f prime of 0 if z is equal to 0, then one can easily conclude that g is analytic on full domain D. That is the first step. Okay. Then what I will do, so I have this open unit disk, so this is my open unit disk, so this is radius 1, okay. Then what I will do, so I am taking a r which is 0 less than r less than 1, strictly less than 1, and then I am considering the closed disk of radius r, so that means I am just considering another disk of center 0 radius this times r, and I am considering the closed, that means I am including the boundary as well, right. So that's why I am saying d bar of r, that means all those z belongs to C such that modulus of z is less or equal to r. Okay, suppose you consider this dr closure. Now since f from D to D is given, then what is that? The image of f of z should be strictly less than 1, because what is my D? D is nothing but all those z is in C such that modulus of z is strictly less than 1. Now if I take z, it maps to f of z, and f of z belongs to this set, so that means modulus of f of z which is strictly less than 1. So that is the first observation, and this is true for all z. This is because of the fact that f is a map from D to D. Okay, that is one. So therefore in particular, if I take mod z is equal to r, that means if I take a point here, that means it is a point in the disk, so this is my full disk mod z less than 1. If I take a point in the boundary of mod z is equal to r, so this is a point in D. So therefore if I take the estimate modulus of g of z where mod z is r, that means g of z, how I define fz by z if z is non-zero, because mod z is r, so therefore z is non-zero, so therefore this is fz by z, which is mod fz by mod z. That means which is mod fz by r, because I started with mod z is equal to r. Now look, z belongs to where? Z is in mod z is equal to r, so that means z is in D, and in D modulus of f of z is strictly less than 1, so therefore this is strictly less than 1 by r. So therefore if mod z is equal to r, if I take the estimate of g of z which is exactly strictly less than 1 by r, so that is the first observation, and hence this is true. That means modulus of g of z which is lesser equal to 1 by r for whenever mod z is equal to r. See, it's okay, fine. So I am saying that, so for mod z is equal to r, so this is the kind of estimate I am having. So therefore I have a function g, right, I have defined, which is analytic on D. If I take dr closure and if I take mod z is equal to r, then I'm concluding that modulus of g of z which is lesser equal to 1 by r, and as long as mod z is equal to r, because of this kind of estimate. Okay. Now you will see, now I will apply what is called maximum modulus principle. Now what is your g? Your g function is analytic on D. So in particular g is analytic here. So that means g is continuous on dr closure, that means this is the including boundary dr closure, it is continuous. It is analytic on dr, there is no closure, that means it is analytic here. Okay. So therefore g is continuous here on the closed dr closure, g is analytic here. So therefore by maximum modulus principle it says that if it attains maximum, it attains only on the boundary, that means it attains only on mod z is equal to r, but on mod z is equal to r, g of z is dominated by 1 by r. So therefore by maximum modulus principle I can say that modulus of g of z which is dominated by 1 by r for all mod z strictly less than r, right? Because you see, because mod z is less than r, that is the interior of the disk mod z, mod z is strictly less than r, right? So that means if I consider this set dr closure, what is the interior? Interior is this set d of r which is z is in C such that mod z is strictly less than r, right? But on the boundary, that means on the circle of mod z is equal to r, my function g of z is dominated by 1 by r, and you know by maximum modulus principle says that if g attains, modulus of g attains maximum, it should attain, if it has a maximum it attains on the boundary, and on the boundary it is dominated by 1 by r. So therefore if I take any point z in the interior, that means in the set d of r, it has to be dominated by any value of the functions g on the boundary, and on the boundary it is dominated by r. So therefore this premise is true, and that is exactly I have written in my next slides. Look, since G is analytic in D, so therefore it is analytic in an open set containing the closed disk D of R. So okay, it proves in this way. So because to include mod Z equal to R, what I am saying is this one. So this is my mod Z, so you can say this is mod Z equal to 1, so this radius 1, so take a small radius, say R, so this is mod Z is equal to R. So now you consider this set including the boundary, okay, this is I am saying DR closure. Now what is given? G is analytic on whole D, so then it says that I am considering some open set which contains my set what is called set DR closure. Now since my function G is analytic on D, so therefore G is analytic on an open set which contain my closed disk DR closure. I mean this is my closed disk, so it contains in this open set, okay. So therefore now if G is analytic in an open set and it attains, or forget about whether it attains or not, as long as G is analytic in an open set containing my closed disk DR closure, so therefore by maximum modulus principle it says that it should attain maximum only at the boundary, and at the boundary it is dominated by 1 by R. So therefore I can say that modulus of Gz which is lesser equal to R for mod Z lesser equal to R. Okay, so this is where I am applying what is called maximum modulus theorem, because first I have proved that G of Z which is dominated or lesser equal to 1 by R for mod Z equal to R. But this will implies G of Z which is lesser equal to 1 by R for mod Z lesser equal to R. That means only on the boundary how I am concluding that even if I take Z inside the disk, the same boundary will have, and that actually follows from what is called maximum modulus theorem, because my function G is analytic on DR closure or some open set containing DR closure. So therefore if I apply maximum modulus principle, G is continuous on DR closure, G is analytic interior of DR closure, by maximum modulus principle maximum of modulus of G attains on mod Z is equal to R, on mod Z is equal to R it is dominated by 1 by R. So therefore by maximum modulus principle, even if I take mod Z is inside DR, that means modulus of Z is lesser equal to R, the same inequality should be true. That means modulus of G of Z which is lesser equal to 1 by R for mod Z is equal to lesser equal to R. Okay. Now let Z belongs to D arbitrary. If I take any arbitrary Z, choose R in such a way such that mod Z less than R less than 1, then the above equality says that modulus of G of Z which is lesser equal to 1. Anyhow, I am giving the similar kind of same statement. I am again repeating the same things. So okay, so this is done. So therefore since the inequality holds for every R satisfying R is strictly greater than Z and less than 1, now you can guess I am taking R approaches to 1. So that means what I am trying to say is that you have a disk. So you take some point. So you take some point modulus of Z, some point Z. Take the modulus of Z. Take R in between 1 and modulus. So since modulus of Z is less than 1, so therefore I can always have the existence of R which is in between modulus of Z to 1, and then I can apply the whatever argument I have given, that modulus of Gz which is lesser equal to 1 by R, because modulus of Z is lesser equal to R, right, or strictly less than R. So therefore I will have this estimate. So this then I can apply, and since it is true for R, so therefore if I take R approaches to 1 minus, so therefore I can say that modulus of Gz which is lesser equal to 1, because 1 by R approaches to 1 as R approaches to 1 minus. So what is that? R approaches to 1 minus means R is a positive number. So this is my 1. So this is my 1. So that means R approaching to 1 from the left of 1. That means that is the meaning of 1 minus. That means R approaching to 1 but from the left. So therefore in pictorial you can see that. So this is what I would like to see. So what I am trying to say is the following. Okay, so this is my open unit disk. So this is of course 1, this is R. Okay, so if I take Z from here, mod Z is less than R, then what will have? I will have this estimate, and then since I am taking R in between mod Z and 1, so therefore I can say that let R approaches to boundary. If R approaches to boundary, then I am saying that modulus of gz is less or equal to 1. R approaches to boundary means what? I am taking, so because if I take z from here, so what is modulus of z? Modulus of z approaches to 1, na? So therefore, whatever z I can take inside D, so and so that means if it is here, then there is no problem. Mod z is less or equal to R, you will have this kind of estimate. But if z approaches to the boundary, that means modulus of z approaches to 1, and since R is greater than modulus of z less than 1, so therefore it will implies mod z approaches to 1 implies that R is approaches to 1 from minus. That's what it says. Now R is approaches to 1 minus, that means modulus of gz which is less or equal to 1. So what I am trying to say is that using maximum modulus principle and using the way I have defined my function g, which is analytic on D, not only that, the image of g of the open unit disk, that is actually dominated by 1. That's what I am trying to say. Okay, so it is clear. I think this is clear. So first you have the functions f from D to D, f0 is equal to 0. I want to show that modulus of f of z which is less or equal to mod z. How I can do that? So I am defining a new function or some auxiliary function, that is g, which is fz by z if z is non-zero, equal to f prime of 0 if z is equal to 0. So now if I look at the analyticity of my function g, at z is non-zero but z is coming from D, my function is analytic. So only you might think it will have some singularities at the point z is equal to 0. But the way I have defined my function g at the point 0 by g of 0 is equal to f prime of 0, I can remove that singularity. That means g is analytic on the full domain. Then I am using maximum modulus principle. I am taking the point z inside D, that means modulus of z is less than 1. I am taking R, which are having this kind of properties, mod z is strictly less than or less than 1. Then I am considering the closed disk dr closure. There I am having the function g which is continuous inside dr closure, that means inside di it is analytic. So therefore by maximum modulus principle, my maximum of modulus of g attain on the boundary, that means mod z is equal to r. But in mod z is equal to r, by definition, by the way I have defined my function g, which is always dominated by 1 by r. So therefore by maximum modulus principle, if I take mod z is less or equal to r, it will having this kind of properties, mod z is less or equal to 1 by r. Now what I am doing, since I am taking z any arbitrary point in D, so therefore if I take z, z is very near to the boundary of D, that means if mod z approaches to 1, which will implies r approaches to 1, that means if I take r approaches to 1 minus, I will conclude that g of z absolutely is less or equal to 1. So therefore if I take any point z inside D, then modulus of g of z which is also dominated by 1. Once I have this one, then consequently because g of z which is of the form f of z by z, then you will have this f of z which is z times modulus of gz. So this is implies f of z, z times g of z, and this is mod z as it is, but modulus of g of z I just proved this is less or equal to 1. So therefore this is less or equal to modulus of z. So and therefore I will have the inequality modulus of f of z which is less or equal to z, and for every z in D. So what about at z is equal to 0? Since at z is equal to 0, I am defining g of 0 is equal to f prime of 0. So therefore by the fact that g of z is less or equal to 1 for all z, which will implies f prime of 0 which is g of 0 which is less or equal to 1, and therefore we will have derivative of f at the point 0 which is also modulus is less or equal to 1. So that means I have proved these two conclusions. So that means if I have a functions d from D to D analytic, then first conclusion this one, fz by z or modulus of f of z which is dominated by modulus of z for all zd, and second one is that derivative of f at 0 which is less or equal to 1, because g of 0 is less or equal to 1 and g of 0 means what? That is f prime of 0. So therefore this is true. Okay, so if I take any point z inside D, okay, x at the point z is equal to 0, then of course modulus of g of z which is less or equal to 1 implies modulus of f of z less or equal to z, and if I take z is equal to 0, that means I will have g of 0, and g of 0 is less or equal to 1, that will implies f prime of 0 less or equal to 1. So therefore these two conclusions I am done. Okay, so this is done. So now next part is that suppose you assume that f of z is exactly equal to modulus of z for some z, or say f prime of 0 absolute is 1. Then I have to show that it will of the form f of z is equal to az where modulus of a is 1, and that also again follows from maximum modulus principle. Why? Because you see it remains to prove the equality case. That means first we assume that there exists a point z naught in D such that z naught is non-zero because it is inside D, and z naught is non-zero such that f of z naught absolute is exactly equal to modulus of z naught. Okay, so what I am saying is that this is your open unit disk, except 0 take some point z naught inside D such that f of z naught, which is exactly equal to modulus of z naught. Now if this is the case, then what is the value of modulus of g of z naught, which by definition f of z naught divided by z naught absolute, and since f of z naught mod is same as mod z naught, that means modulus of g of z naught is exactly equal to 1. But we already have proved that the function g, which is analytic on D and which is dominated by 1 for every z in D, right? So therefore g is analytic in D and modulus of gz, which is dominated by 1 for every z, and inside the point, so this is the kind of what upper bound, right, and it attains the bound in the interior. So that means, look, so what I'm saying is that now therefore mod g attains its maximum, so this is the maximum value inside my domain, okay, in the domain. So that means I have a function g which is analytic on domain D, so therefore if it attains maximum, it should attain on the boundary, not on the interior. But look, so if I can say that this is, so that means what? That means if suppose this is true, then I am saying that g of z, which is lesser or equal to g of z naught, and this is true for all z in D and z naught in D. But which should not be the case, right? This should not be the case, because what is your maximum modulus principle says? Maximum modulus principle says that if I have an analytic functions open unit on open unit disk, and suppose the maximum of modulus of g attains or it occurs, then it has to attain on the boundary. That means you cannot have or you cannot get any point z naught in D such that modulus of gz, which is lesser or equal to modulus of g of z naught for all z in D. But if I assume that there exists a point z naught is non-zero such that this is true, but I am having the existence of one point z naught inside D such that this is true, which contradicts the fact maximum modulus theorem, and that means this will imply that your function g has to be constant. There is no other choice. So therefore that's what I have written. Since mod g attains its maximum value 1 at the interior point, okay, because at the interior point z naught is equal to non-zero, I am having the equality, which implies this kind of equality, and you by maximum modulus principle you cannot have any existence of any point z naught which are having this kind of properties. When this will happen, you have only one choice, that g is constant. So that's what I am saying. So therefore by the maximum modulus principle or maximum modulus theorem, g has to be a constant functions. So therefore there exists a constant c such that gz is equal to a, and this is true for all z in D, right? So I think it is clear, right? So same thing, earlier one, by applying maximum modulus principle, I will have the estimate. Again here the same, I am applying maximum modulus principle. If I assume that there exists a point z naught inside D, suppose z naught is non-zero, and you have this equality, which will implies the function g satisfies this kind of inequality at some interior point z naught inside D. But by maximum modulus principle says that you cannot have the existence of any z naught inside D which satisfies that modulus of gz, which is lesser or equal to modulus of g of z naught for all z in D. When it is possible? Only when g is constant. So that's what I am saying. So therefore modulus of g attains its maximum value 1 at the interior point, right? Because of this fact, which is possible only when your g is constant. So therefore assuming that there exists a such that g of z is equal to a. Now g of z is equal to a means what? How g of z looks like? F of z divided by z. So therefore it says that since g of z naught, okay, it says that, so first I am trying to get the value of the absolute of the complex number a. It says that since g of z naught absolute is 1 because of this fact, and g of z is equal to a for all z, so in particular modulus of a is 1. So therefore you will have g of z is equal to a and modulus a is less than 1. But how gz is looks like? F of z by z is equal to a and modulus a is equal to 1. That means your f of z, which is exactly equal to a times z, where modulus of a is 1. So that's what I am written. So therefore f of z, which is z times g of z, and g of z is equal to a times z for every z. So therefore you will have fz is equal to az and modulus of a is exactly equal to 1. Okay, so that is the kind of first assumption. If I assume that so this is the one I have proved. Okay, so this is the one. So if fz is equal for some non-zero, if I take any some non-zero z in D, suppose modulus of f of z naught is equal to modulus of z naught, then I will have f of z is equal to az for all z in D. Or you can assume that suppose at 0 f prime 0 absolute is 1. If I assume that fact, then I will show that the same conclusions will hold. Okay, so if I go back this one, so I am done. So this is the one. So finally, suppose, so if I take any z naught inside D and Z naught is non-zero such that absolute of f of Z naught is equal to modulus of Z naught, which will implies your A piece looks like this one. That means f of Z is equal to AZ, modulus A is less than 1. Now if I assume modulus of f of 0 is equal to 1, then same thing will happen. Instead of Z naught, now this time the functions having these properties at the point 0. Now look, so I have defined g of 0 is equal to f of 0. So what is modulus of g of 0? Which is modulus of f prime of 0, and modulus of f prime of 0 is 1. So therefore this is 1. So again the same apply the what is called maximum modulus principle. Now your g of z, which is lesser or equal to 1 for all z in D, and you have a point 0 interior point inside the domain D such that modulus of g0 which is exactly equal to 1. That means it will implies modulus of g of z which is lesser or equal to modulus of g of 0, and this is true for all z in D. Now g is an analytic function on a domain D, and you have a point 0 which is an interior point in D such that g of z which is dominated by modulus of g of 0 which is true for all z in D. But what maximum modulus theorem says, you cannot have any point inside D which satisfies this kind of inequalities. So that means if this is true, then you have only one choice, that g is constant. Okay, same thing again, since modulus of g of z which is lesser or equal to 1 for every z, so therefore the function's mod g attains its maximum value at the interior point. So therefore by the maximum modulus principle, g is constant. Again g of z is equal to a for some constant. Again the fact that g of 0 modulus is 1, we can have mod a is 1. So therefore your f of z is equal to z times g of z, and g of z is a. So therefore you have a of z, and modulus of a is less than 1. So in any case, if z is non-zero such that f of z naught absolute is exactly equal to modulus of z naught, it will implies my functions fz of the form a times z where modulus a is less than 1. Or if I say that modulus of f prime of 0 is exactly equal to 1, then it will implies that your functions f has to be of the form a times z where modulus of a is less than 1. For the first case, you can apply your maximum modulus principle, because at the interior point z naught which is non-zero, which satisfies the properties that modulus of gz which is lesser or equal to modulus of g of z naught for all z in D, which will implies by maximum modulus principle that g has to be constant. And in the second case, if I assume that absolute of f prime of 0 is 1, which will implies that modulus of g of z which is lesser or equal to modulus of g of 0, g at the point 0, and this is true for all z in D. Again by maximum modulus principle, you cannot have the existence of any interior point or any point inside D which having these properties. When it is possible, when g is constant, then also you can conclude that f is of the form a times z where modulus of a is equal to 1. So in any case, so then therefore if either f of z is equal to mod z for some non-zero, or modulus of f prime of 0 is equal to 1, in both cases your f looks like explicitly. That means you can have the explicit expression of your f. How it looks like? It is of the form a times z where z belongs to D and modulus of a is equal to 1. So therefore this is the proof of Schwarz lemma, and it's a nice applications of maximum modulus principle. So kind of if you get the idea is very clear. So if I have analytic functions from D to D having the properties that f of 0 is equal to 0, then you have to show that the growth of f of z is dominated by modulus of z, and f prime of 0 absolute is lesser or equal to 1. How do you proceed? So first, instead of dealing with the functions f, you have to deal with an auxiliary functions, or define a new function g which is fz by z if z is non-zero, and at 0 you define derivative of f at 0, because f is analytic at the point 0, so therefore f is differentiable, so you can define it. So having once you have defined your function g in this way, first you conclude that your function g is analytic on D. Second, by maximum modulus principle, you prove that value of g of z which is dominated by 1 for all z inside D. So therefore from the functions f, now you have the function g which is analytic on D, and g of z absolute is lesser or equal to 1 for all z in D. Once I have that one, then this will implies two fact that because g is of the form f of z by z if z is non-zero, and and f prime of 0 is z is equal to 0. So from the expression of g, first I am concluding that f of z is dominated by mod z, and f prime 0 is lesser or equal to 1. That is the first step. So that means you should apply maximum modulus principle on g to have this kind of expression. Second part is that suppose you have the equality occurs, that means f of z naught is exactly equal to modulus of z naught for some z naught non-zero in D. If these things happen, again by applying maximum modulus principle, you can conclude that f of z is az, where mod a is less than 1, mod a is exactly equal to 1, and if I assume that or modulus of f prime 0 is exactly equal to 1, there also you can apply maximum modulus principle to conclude that f of z is equal to az and modulus a less than exactly equal to 1. So you have the explicit expression of your f. So therefore, very nice applications of maximum modulus principle or maximum modulus theorem, you can have the proof of Schwarz lemma. So Schwarz lemma is very nice. In fact, it tells you explicitly what will be your f if f is analytic from open unit disk to open unit disk, satisfying the property that f of 0 is equal to 0. Then how the it should not be an arbitrary functions, it will have some restrictions. That means growth is restricted by growth of z, and derivative of f at 0 is lesser equal to 1, and in case suppose the equality occurs at some point non-zero point z naught in D, modulus of f of z naught is modulus of z naught or modulus of f prime 0 is equal to 1, then you can say that you will have the explicit expression of f, which is nothing but a times z, where modulus of a is exactly equal to 1. That means 1 degree polynomial. Okay. Not only polynomial, it will have no constant coefficients. Then it is of the form a times z, where mod a is equal to 1. So now I come back to the last nice theorem, which is called Morera's theorem. So this is another beautiful theorem in complex analysis. So what it says is that, again, this is the Wikipedia page, you can have the more informations of mathematicians Morera. So he actually Italian engineer and mathematicians, he works in Morera's theorem and theory of complex functions and complex variable, and he works in the theory of what is called linear elasticity. Okay, so what is that theorem says? So for example, what is Cauchy-Goussard theorem? If you remember, so if I have a like simply connected domain, and if I take any simple closed contour, and if suppose my function is analytic, then the corresponding line integral or contour integral is 0. So now Morera's theorem is somehow giving the converse of that. So suppose you have a suppose nice domain D is there, say like simply connected, and suppose instead of analyticity, suppose you started with a continuous functions, and suppose it is given that if I take any simple closed contour, the contour integrations of f over this simple closed contour is 0, whatever simple closed contour you can take, then it will imply that your function's f has to be analytic. Right? So Cauchy-Goussard theorem says that start with a nice domain, start with a simple closed contour, then the contour integrations over simple closed contour is 0. Morera's theorem is the converse one. That means if I give some domain and if I say that you start with a continuous functions, so if I give that kind of problem, prove that f is analytic, what kind of theorem you should use? Either you can use the classical definitions, using the definitions of analytic functions, you can do that, or you can use Morera's theorem. That means what you have to do, take any simple closed contour, calculate the contour integrations, and if you say that whatever simple closed contour I am taking, the corresponding contour integration is 0, that means you can say that by Morera's theorem your function has to be analytic. Okay. So that's what it is. So the following theorem is some sort of converse of Cauchy-Goussard theorem. By looking at the statement of the theorem, it will be clear. So if a function f is continuous in a simply connected domain D, with the property that the contour integrations of f over any simple closed contour is 0. Look, this is 0 for every simple closed contour C lying inside D. Then you can conclude that your function's f has to be analytic. Now you can, I have discussed this kind of proof earlier, because if I have the assumption that f is continuous and the contour integrations over any simple closed contour sitting inside my domain, that contour integration or line integral is 0, then it will imply that my contour integrations is path independence. That means if I have this kind of domain and if I have this kind of properties, then if I fix a point z0, then I can take a point z, then I can make sense integrations what is called z0 to z. So suppose this is z0, this is z. And why it's that? Because so from z0 to z I can say that take this contour, suppose C, z0 to z, that means I am saying that this is fw dw is nothing but integration C fw dw. And you can say that, well, I am not interested in the contour C, I am interested in this contour D, starting from z0 ending at d. Is it same as integration d f of w dw? Answer is yes, because it is given that whatever simple closed contour I am taking inside D, this contour integration or line integral 0, which will implies that whatever contour I can take starting from Z0 ending at G, the corresponding contour integration or line integration is independent of the choice of the contours. That means whatever contour I can take, as long as it starts from Z0 ending at Z, it will give the same value. That is why I can make sense of this kind of integrations. So if you remember, that kind of part I have already discussed. So because of the fact that integration C fz dz is 0, and this is true for all simple closed contour, so for fixed Z0 in the domain D, I can define this kind of indefinite integration. That means capital of f of z, which is Z0 to z fw dw. What is the meaning of that? This is nothing but the same as contour integrations over C f of w dw, that you know. And what is the contour? Contour is any contour you can take starting from Z0 and ending at Z. That's it. So that means this object is nothing but this is the contour integrations. C is any contour starting from Z0 and ending at Z, and whatever contour you can take, it will give the same value because of your assumption. So therefore this indefinite integral makes sense, and actually this is the antiderivative. You can see when I talked about antiderivative, this is the antiderivative. So therefore this capital F is perfectly alright, well defined. The next part is I will show that this capital F is differentiable, and capital F derivative is nothing but your function small f. Okay. Note that, so first observation is that, note that capital F of z is well defined because it is giving the same value whatever contour I can take because of my assumption. Only part is remaining that I have to show capital F prime is equal to small f, and just use the definition. So that means you have to prove that limit delta of z. So that means you have to show that this. First you calculate this object and show that if delta z approaches to 0, this approaches to actually f of z. That's it, that's the only thing. So this you just calculate the expression f of z plus z delta z minus f of z, which is nothing but z to z plus delta z f of w dw, but you have to be always careful. What is the meaning? That means whatever contour I can take starting from z ending at z plus delta z, this is the meaning. And this difference you can prove exactly equal to this one I have already discussed using the properties of the contour integrations. So therefore you will have the expression here. That means this is actually z0 to z plus delta z, right? And what is it? This is z0 to z, f of w dw, this is f of w dw. But this difference is exactly equal to z to z plus delta z. By using the properties of contour integrations, you can have this expression. So therefore if I take the divisions of delta z, you will have this kind of expression, but you can have that z to z plus delta z dw. That means if I integrate with respect to constant functions 1, by definitions of contour integration, it turns out that it is nothing but the increment delta z. So and having the properties that f of z is equal to this one, I can write my f of z, which is a constant. So this is the integrand constant will be there, you can take outside. So what will remain is that z to z plus delta z dw, which is exactly equal to delta z. So therefore this expression I can write it there. So then what, so see at the end of the day what I have to do, I have to take delta z approaches to 0 and so that this object converges to small f of z. So I will have the expression of this, then I will take the minus f of z, and since f of z has this kind of expression, so I can take the difference in between and have to estimate. Look, so if I have the, I already have the expression of this object by this one, and I know the expression of f of z by this one, so you have to just combine it. If I combine it, you will have this kind of expression. 1 by delta z will be outside, and then you will have z to z plus delta z of this object. Now what we have to do? I have to estimate. So if I take the absolute in the left hand side, you will have the absolute here. So somehow I have to put absolute inside the integrand, and that you can do that by properties of contour integrations. So therefore I can put this absolute inside, and inside you will have absolute of f of w minus f of z. But what is f? F is continuous given. So now I have to use the continuity of my f at the point z, and using the continuity I can conclude that this absolute goes to 0 as delta of z approaches to 0, then I am done. So that's exactly I have done. Since f is continuous at the point z, given epsilon there exists a delta such that whenever w minus z is less than delta, then f of w minus f of z, which is less than epsilon, this is because of the continuity. So therefore what is w? W lies between z to z plus delta z. So now this is a contour integrations. So what you do, suppose this is your contour, so this is z and this is z plus delta z. You just take, see you have to take any contour starting from z ending at z plus delta z, right? So you can say that, okay, I am considering this integration over L f of w minus f of z dw. This contour integration I will take. What is my L? L is the line segment, that's it, starting from z and ending at z plus delta z, right? So if I take L is there, and if I take any point w inside L, then what is the distance between w minus z, which is same as lesser equal to w minus z, which is dominated by z minus z plus delta z, right? And which is dominated by what is called modulus of delta z. And if I choose modulus of delta z is less than delta, that means modulus of w minus z is less than delta. That's exactly. So if modulus of delta z is less than delta, that means modulus of w minus z is less than delta. By continuity, I will have fw minus f of z. That distance is less than epsilon. So therefore, if I take the absolute of this one, you can push the absolute inside the integrand because of the properties of contour integration. That's why I'm putting the absolute in the integrand. And if I just use the, because this integration over is nothing but integrations over L of this object, na? Because I'm taking one contour. So okay, so this is as the notations. So this is, you can say that this is dominated by, because this integrand will come out as epsilon. So you can take out epsilon, and what will remain is that integrations over L, and then you have dw mod, and it will give you actually modulus of delta of z. That means, what is this? This is the length of your curve. Now if I take a line segment from z to z plus delta z, then what is the length of the curve? It's absolute of delta z. So therefore this is absolute of delta z, this is absolute of delta z coming from here, it will get cancelled, so what will remain is that epsilon. So finally what we have proved is that I can make this object less than epsilon whenever mod z is less than delta. So if mod z is less than delta, and that is nothing but the what is called, if I have this object, I can make less than epsilon whenever mod z is less than delta. That means limit delta z approaches to 0, this object converges to f of z. That means my function's capital F is differentiable, and derivative of f at z is exactly equal to f of z. This simply implies that capital F is analytic functions. Since capital F is analytic, you know all derivatives exist and all derivatives are analytic. So therefore the derivatives fn z for all n exist, they are also analytic. Since fn so is nothing but fn minus 1 of z, so therefore for each n f is also analytic, and this completes the proof. Correct? So therefore it is okay. So therefore f prime of z is equal to small z. That's okay. That means I am proving that capital F is analytic. Now since capital F is analytic, so all the derivative of capital F exists, and that is also analytic. So if I take the second derivative, that means what is that? This is f prime. That is exist. So that, and that is also analytic. That means f prime is analytic, f double prime is analytic, and so on and so forth. So therefore my functions f is analytic. What is the definition of analytic functions? It is differentiable, right? So because of the fact that capital F is analytic and capital F prime is equal to small f, so if I take the capital F double prime, that means my f is differentiable, and it is differentiable infinitely many times. So therefore my function small f is also analytic. So therefore this is the proof of what is called Morera's theorem by just simple applications or using the definitions of derivative. But you have to be little careful. The assumption it is given, it's very strong assumption. That means it is continuous, given perfectly all right. On top of that, it is given that if I take any simple closed contour inside domain, the contour integration is 0, which will implies that I can define my functions capital F, that means these independent integrations. And then its function is well defined, and then later on you will show that this capital F is differentiable, and derivative of capital F is exactly equal to small f by using the continuity of small f. And then since capital F is analytic, it is infinitely many times differentiable, each derivative is analytic, which will implies that my function small f, which is also analytic. So somehow this theorem is actually converse of Cauchy-Grushev theorem. If I have an analytic function on a simply connected domain, any simple closed contour if I take, then the corresponding contour integration is 0. Start with the continuous functions on a simply connected domain, assuming the fact that contour integrations on any simple closed contour of my function f is 0 implies my functions small f has to be analytic. Okay, so I think that's all for this week lectures. So therefore we have learned many nice theorems, like we have learned what is called Liouville's theorem, we have learned maximum modulus theorem, and many applications of say Liouville's theorem. I have discussed problems, using Liouville theorem, we will have fundamental theorem of algebra. Using maximum modulus theorem, we will have very nice theorem called Schwarz lemma. And then finally, I have discussed what is called Morera's theorem, some sort of converse of Cauchy-Goussard theorem. So these are very nice theorem in complex analysis, and using that theorem, you will be able to solve many nice problems. So maybe couple of problems you will see in your assignment, and maybe in the exam you will see some of the problems will be there using those kind of theorem. So I think I should stop here for this lectures week. So this is done here. In my next lecture, my plan is to talk about, or I will start the definitions of what is called Taylor series. So you will see if I have analytic functions, it will have a Taylor series expansions. In fact, some books they started with analytic functions by saying that it will have a Taylor series expansions, but I started with something else, and then I will show that when I will have the notions of series in terms of series expansion, the definition of analyticity and power series expansion or Taylor series expansion, both are equivalent. Okay. So in my next lecture, in fact next week lecture, I will start with what is called power series. I think I should stop here. Thank you.